Let's keep taking a look at these exponential functions and see what else we can learn about them. So let's take a look at this slide and try to understand what this is all about. So exponential functions are not linear. Linear functions are created by adding or subtracting the same value over and over again, not exponentials. It's through the process of multiplication. So if you look at this carefully, look what growth is. Growth is when the number is greater than 1, like maybe 1.50 or something like that. Decay, on the other hand, is when you multiply by a number that's less than 1, like maybe 0.5, something of that nature. So let's see if we can determine whether each table represents exponential growth, exponential decay, or maybe even neither. So you want to look for a pattern. So what I'm looking for in this instance is that my x values are all increasing by the same amount. Well, the question is, what is happening to the output values, the y values? Can you determine that? Well, if it is exponential growth, then we know it's created by a process of multiplication. So I'm wondering if we take a look at a couple numbers that are next to one another, can you determine what the multiplication factors between those? I can, but I wonder if you can. What you should do is you should take those numbers and divide them in reverse order. So what you should try to do is this: 90 divided by 270. And that will give you what's called the common ratio. Let's see if we can figure that out. So it'd be 90 divided by 270. And that's 0.3 repeating. You could change that to a fraction if you have a key that allows you to do that. That's 1/3. So my pattern here is multiplying by 1/3 over and over again. I need to test it to see if that actually works. So let me go to my calculator, and you probably remember doing this before. Okay, I'm gonna have trouble making this thing move over here, I bet. And it won't do it for me. Okay, well, I'm just gonna do this. So if I put the first number in at 270, press enter, and then multiply that by 1/3, which is the same thing as dividing by 3, do I get all of the numbers from the table? 30, 10, and I do. So the answer to this is yes. This is an exponential function. And what does it indicate? Because these numbers are getting smaller, it's decay. And because this is less than 1, that means it's exponential decay. All right, let's try another one, part B. What do you think's happening here? So the x numbers seem to be increasing at the same amount. Well, let's look at our y values, the output. Can you discover a pattern just by looking at it? I think it looks pretty obvious. This one looks like we are multiplying by 2 each time. So this is, yes, exponential growth, because that pattern works. Keep multiplying by 2. That's plain to see. And since this number is bigger than 1, this is growth. And you can see that these y values are getting larger, aren't they? That's exponential growth. Let's go to the next table. Same problems. I want everybody to try those. Okay, so what do we think here about these y values? Can you find a value? Well, they're getting smaller, aren't they? They definitely are. And if you can't determine what that is, you need to go to your calculator and you need to put in the second number divided by the first and establish a number. 0.25. You want to change that to a fraction, 1/4. Let's see if that works. So I'm thinking that this is going to be the common ratio is 0.25 or 1/4. Is it? Let's test it. Let's see if I get all the numbers from that table. So I'm going to put the first number in, press equals, and then begin the pattern. Multiply it by 0.25 or 1/4. Do I get 16? Do I get 4? Do I get 1? I sure do. So yes, this is exponential growth. I'm sorry, yes, but it's decay. It is an exponential function. It's decay. Let's go to the next situation. Do these numbers increase by the same amount? Yes, they do. What about the y values? What's happening? I don't know about you, but it looks to me like we are adding 7. So that would be a common difference, which means this is linear. It's not exponential at all. So this would be classified as neither, I guess. But it is linear because we have studied that. It's not exponential. How about this set of questions? Determine whether each function represents exponential growth or decay, and then identify the percent rate of change. Okay, so what I need to do is look at this value. That's the growth factor or decay factor. So in part A, 1.07. Well, I got to tell you something. 1.07 could be written as 1 plus 0.07, right? So what that means is this 1 represents 100%. This 0.07 represents 7%. So that is larger than 1. This is growth by 7%. Let's go to part B. Let's take this 0.98. Now, 0.98 is definitely less than 1. So 0.98 could be rewritten as 1 minus 0.02, couldn't it? Think about that. And that means that this number here represents 100% of the original amount. This number as a percentage is 2%. So this is exponential decay because the original value was under 1 and you are losing 2%. All right, everybody try those. Okay, the first one, 0.92. So 0.92 could be rewritten, think of it as just 92 out of 100, as 1 minus 0.08, right? Wouldn't that give you 0.92? Isn't 92 is 8 units away from 100? Sure is. So this number right here represents 100% of the original amount, and it looks like it's losing 8%. So this is exponential decay, losing 8% over and over and over again. 1.2, what's that mean to us? Well, 1.2 could be rewritten as 1 plus 0.2, or in other words, 0.20. It's the same thing, isn't it? So once again, this 1 in Decimal format means 100% of the original amount. 0.2 is not 2%, it's 20%. And that number's bigger, 1.2 is bigger than 0, or than 1. So this is exponential growth. It's going over 100%, where decay is under 100%. All right, now let's take a look at what's called compound interest. Very interesting. This is how bank accounts grow. It's how loans are figured out for cars and houses and boats and motorcycles, etc. So to be able to do these problems, you have to understand this formula. So I want everybody to study it very closely. So principal is the initial amount of money, their starting amount that you put in the bank. R is your annual interest rate in decimal form. So if you got interest at 2%, that would be like 0.02. T is how long in years the money is in the bank. So we're just talking about bank accounts here, not loans. And N is the number of times the interest is calculated per year, or that's called compounding. Let's try some problems. Let's all remember that formula. You might want to write it down so that it's easy to refer to. Okay, here we go. You deposit $100. So what I'm going to do is I'm going to put some notes on here. $100 is your principal, okay? In a savings account that earns 6% annual interest. So this is your rate, but it's got to be written as a decimal. That'd be 0.06. If you write 0.6, that means 60%. Write a function that represents a balance after 1 year. That's the T, and calculate it. All right, let's go to it. Let's go to part A, compounded monthly. So how many months are there in a year? Okay, now that means N is 12. So what we do is we go to our formula. And what I'm going to do is I'm going to write it down one time here. Oops, I made a mistake here. And then we're just going to substitute. I'm going to write it up here actually. Amount of money is your principal times 1 plus your interest rate divided by the compounding periods times N times T. All right, let me move this up here. Okay, here we go. The first one, Y equals my principal. 1 represents 100% of that $100, plus my interest rate, which is 0.06, divided by N, which is 12, raised to the 12 times 1. 1 year. Now that's just the number 12 then, isn't it? Okay, so what we do now is we get our calculator out and we figure that out. So very carefully type this into your calculator. This is exactly how a bank account is calculated. See how I'm doing this? 0.06. Now I'm going to use the division key. You could use a fraction key if you want. Close your parentheses. You must use an exponent key at this point. Now 12 times 1 is just 12, isn't it? So I'm just going to put a 12 in there. All right, so my answer will be approximately 106.17 because I'm rounding to the 100th. So if you put $100 in a bank account and get 6% interest, and the interest is calculated every month, you end up with a little bit more than $106. So you've made about $6.17 just by keeping the money in the bank. All right, so let's go through a couple more here. So this formula is going to be the same every time. The only thing that's going to change is n. So in this case, it's yearly. So that means n will be 1. In part C, it's compounded quarterly. Quarterly means 4, doesn't it? So 4 times a year, every 3 months. And semi-annually, do you know what that means? That means twice a year, once every 6 months. So it's the same exact formula. The only thing that changes is the value of n. So I think what I'm going to do is I'm going to use some magic with a smartboard. And I think I'm going to try and highlight this whole formula here. We're pretty darn close to the whole thing. So bear with me. And then I'm going to erase part of this because part of it will not be the same. Okay, so I just messed that up, didn't I? Okay, so the final amounts will be different. And what else will be different? Well, my value for n will be different. So this and this are going to be different. Excuse me, for each one of these problems. What remains the same is the principal. You're always going to invest $100. Interest rate is staying the same, and it stays in the bank for 1 year. So the only thing I'm going to change would be how many times it's compounded. So for the yearly, it's just going to be a 1. So I'm going to go to my calculator, and if you know how to edit, you could just edit this equation. I think I'm going to try to do that. So if I arrow up, press enter, it gives me this equation again. So my exponent is just going to be 1. And my denominator is just going to be a 1. So compounded 1 time a year is going to be $106 and 0 cents. How about quarterly? Well, that's 4 times per year. So that'll go there and there. Let's do that calculation again. So I think what I'll do is I'll just bring up my calculator and I will edit this equation again. And this exponent will now be a 4 times 1, or a 4. And the denominator will be a 4. So this is pretty interesting. If you have a bank account or you invest money, this is exactly the way this works. $106.14. So these are all different amounts, aren't they? Now they're slightly different. We're not talking about an amount of money that is huge, but think if you're talking about thousands and thousands of dollars, certain things can impact how much money you make. Now let's start thinking about what that is, and we can have a quick discussion about it. Okay, how about our last one here? Part D, semi-annually. Well, that's twice per year. Let's go ahead and put that information in the calculator and see what we get now. So I'm going to once again edit my equation. And now my exponent will be 2 times 1, or just 2. And my denominator of the fraction will be a 2. And what's this amount? $106.09. So I've got a question for you then. You look at this. Which one of these situations yielded the most money? Look very carefully. And I'm going to say it was compounding monthly. It gave us a little bit more money than everything else. And what was the second best situation? Well, I'd say it's compounding quarterly. Look at that. It gave you the next best. And then what's the next one after that? That's right, semi-annually. So the moral of the story is if everything stays the same and you can change anything, I guess it would be the compounding periods. The more often you get interest calculated, the more money you will get. Another way to increase the amount of money you get, a better interest rate, a higher interest rate, things of that nature.